Three amateur radio operators, continents apart, each intercept a burst on 1420 MHz, the hydrogen line. It matches Andromeda's coordinates, echoes across software-defined radio logs, and fits a pattern meant to be solved. The world has relied on professionals, but this time amateurs crack open a cosmic riddle, and what they decode leads to more fear than awe. In amateur radio operators decode Andromeda signal fragment. Wish they hadn't. The question isn't just what's out there, but whether humanity was meant to listen. So, what did we really receive that night? A sudden spike at 1420.40575 MHz slices through the static timestamp 02713 UTC in an Ohio basement. The operator's hand hovers over the SDR controls, eyes flicking from the waterfall display to the logbook. Narrow band, barely wider than a whisper. The signal sits right at the hydrogen line, where Earth's radio astronomers have listened for decades and rarely found anything that couldn't be explained. A quick check rules out local interference. The log records: dish, azimuth 38.2 degrees, 2 degrees elevation 61 degrees, Andromeda's coordinates locked in. The operator's voice caught on a Discord call is clipped and urgent. Anyone else seeing this? 6 hours ahead in Berlin, the same frequency lights up on a home-built receiver. The signal's phase and drift match the Ohio trace within milliseconds. The Berlin operator, a software developer who scripts his own FFT scans, scrambles to cross-check with archived satellite passes and RFI logs. Nothing matches. The hydrogen line is supposed to be quiet, protected even from terrestrial transmitters by international law. He posts a screenshot to the shared forum overlaying UTC frequency and SNR. Confirmed, not local, not known artifact. Melbourne's radio room is cluttered with cables and a battered logbook. There, the operator waits for Andromeda to clear the horizon, catching the signal at its faintest, just above 10 degrees elevation. The SDR's gain is maxed, the noise floor dancing, but the same narrow spike appears, identical in frequency and timing. The operator's first reaction is disbelief, a muttered curse, then a frantic scroll through RFI databases and a check of the weather station's logs. The timestamp is 131,459 UTC, just as predicted by the others. He uploads his raw data and joins the call. That's 3 continents, same event. This isn't us. Within 90 minutes, the Discord channel fills with screenshots, UTC logs and raw IQ files. Operators compare antenna patterns, system temperatures and calibration notes. No one can trace the signal to a known source. The initial thrill in their voices is edged with something else. A sense that whatever they've caught, it wasn't meant for them alone. The search for independent confirmation has begun. But the signal's origin is no longer just a curiosity. It's a shared mystery echoing across the globe, demanding answers none of them are sure they want. Screens fill with waterfall plots and UTC-stamped logs as the Discord channel surges to life. Operators in Ohio, Berlin, and Melbourne upload raw IQ files, each file paired with calibration notes and antenna diagrams. The group's first priority: rule out any possibility of terrestrial interference. They check GPS-disciplined clock traces, confirming timestamps align within fractions of a second. Environmental telemetry, temperature, humidity, even local RF noise levels, gets posted alongside the signal data. Each site's antenna log details azimuth and elevation, showing dishes aimed precisely at Andromeda's coordinates as the galaxy rose above the local horizon. In Melbourne, the signal's arrival comes hours after Ohio and Berlin, matching the galaxy's slow sweep across the southern sky. The staggered detections spaced by Earth's rotation strengthen the case for a sky-based origin. No satellite pass, aircraft, or known terrestrial emitter lines up with the signal's path or timing. A volunteer in Tokyo monitoring the Discord pulls up NASA's latest satellite catalog and cross-references every possible source of interference. Nothing matches. In the shared folder, a spreadsheet grows with each new entry: UTC, SNR, dish size, system temperature, and operator notes. By the end of the day, more than a dozen independent logs show the same narrow spike at 1,420 MHz, drifting only as expected from Andromeda's radial velocity. Geolocation filtering becomes the group's informal protocol. Only detections with the galaxy above 10 degrees elevation and with matching Doppler corrections for M31's approach are counted. The pattern holds across hemispheres, from Germany's urban outskirts to a sheep farm outside Melbourne. The evidence is now layered. Not only is the signal present, but it tracks with the movement of Andromeda across the sky. The Discord chat, once casual, now reads like a scientific logbook, operators double-checking each other's calibration, sharing code snippets, and debating the best way to package their data for outside review. The sense of teamwork and of something extraordinary unfolding is impossible to ignore. A pattern begins to surface as the raw IQ files are fed through custom fast Fourier transform scripts. One operator, a retired engineer in Ohio, writes a short Python program to search for repetition in the pulse stream. He counts 1,679 distinct pulses spaced with uncanny regularity. The number stands out not just for its size, but for its factors, 23 and 73, both prime. This is the same grid structure used in the 1974 Arecibo message, a deliberate mathematical choice meant to signal intelligence through universal logic. The Ohio operator posts his results to the Discord, and within minutes, others are running their own checks. Berlin's developer overlays the pulse sequence into a 23 by 73 grid, transforming the raw data into a binary bitmap. The image is crude but unmistakable. A spiral shape fills the left side, echoing the arms of a galaxy, while a string of dots and dashes lines the edge. Some see the atomic numbers for hydrogen, carbon, nitrogen, oxygen, and phosphorus, key elements for life, encoded in the pattern. Others speculate about the meaning of a tight cluster of marks near the center, their arrangement too regular for natural noise. The group shares their screens, pointing out each feature, arguing over whether the structure is intentional or an artifact of the decoding. The resemblance to the Arecibo message is impossible to ignore. But the signal source, Andromeda, 2.5 million light-years away, forces them to reconsider what's plausible. The Discord chat is a mix of awe and unease. For some, the mathematical clarity is a thrill. For others, it's a warning. If this is artificial, then someone or something out there knows the same prime numbers, the same chemistry, the same basic math. The mystery now has a shape, and the operators are left to wonder what kind of energy and intent could send such a signal across the gulf between galaxies. A signal traveling from Andromeda to Earth faces a challenge that dwarfs anything in terrestrial radio. The gulf between galaxies is not just vast in distance but in physics. At 2.5 million light-years, about 2.37 times 10 superscript 2 meters, the free space path loss for a 1420 MHz transmission reaches roughly 486 dB. That figure is so extreme it's hard to grasp. For context, even the most powerful radar on Earth would be swallowed by cosmic silence long before covering a fraction of that distance. This loss means that unless the transmitter is unimaginably powerful or the signal is focused with surgical precision, nothing but the faintest whisper would ever reach our planet. An isotropic, all-direction broadcast would require more than 90 quadrillion gigawatts, energy on the scale of a star. That's simply not plausible for any civilization, no matter how advanced. But the math shifts if the transmission is tightly beamed. A transmitter the size of a city or even a planet could focus its energy so narrowly that a signal might survive the journey. With a planet-sized phased array, the required power drops to a few thousand megawatts, still enormous, but within the realm of theoretical engineering for a Type II civilization. The beam would need to be aimed with astonishing accuracy, targeting our solar system across the local group. Even then, the signal would drift, broaden, and weaken as it crossed intergalactic space. On the receiving end, amateur dishes 2 to 6 meters across can pick up hydrogen line emissions from our own galaxy. But a true extragalactic signal would push the limits of even the largest professional telescopes. Only a continuous repeating transmission encoded for maximum detectability stands a chance of being noticed at all. The odds are daunting. The excitement of decoding a structured message is always shadowed by the reality of these numbers. Every pulse, every pixel in the reconstructed bitmap is a reminder that nature is indifferent to our curiosity, and that the universe rarely makes things easy. Before any public statement, every candidate signal claiming an artificial origin faces a gauntlet of verification steps. The IAA SETI post-detection protocols require that all raw data, calibration logs, and metadata be archived and distributed to independent research teams. Each team must run their own analysis using different software and hardware to confirm that the signal's characteristics, frequency, timing, modulation, match across sites and are not artifacts of equipment or local interference. The checklist is exhaustive. GPS-disciplined clock traces, antenna alignment records, environmental telemetry, and system gain calibrations must all be included. Null sky frames and RFI catalogs are required to rule out terrestrial contamination. Instrument scheduling becomes a race against time and curiosity. Professional observatories are notified, but telescope time is scarce and must be justified with clear evidence. Amateurs submit their data to institutional liaisons who coordinate follow-up observations and ensure that all protocols are met. The embargo on public release is not about secrecy but about protecting both science and society from premature claims. Only after independent teams using their own equipment and methods reproduce the detection can the embargo be lifted. The Rio scale is applied to rate the credibility and potential impact of the finding. If the score is high, notifications are sent to the scientific community, relevant government agencies, and international bodies. Until then, discussion is limited to a small circle of researchers bound by the shared responsibility to avoid false alarms. The process is slow by design, shaped by decades of lessons learned from past missteps. Scientific caution in this context is not a barrier, it is the foundation of trust. In 1967, a young researcher named Jocelyn Bell Burnell noticed a regular pulsing in her radio telescope data. The signal was so precise, pulsing every 1.337 seconds, that it briefly carried the label Elgium-1, for little green men. The excitement was real, but the answer was natural. The first discovered pulsar, a spinning neutron star, not a message from another world. A decade later, a different mystery arrived. On August 15, 1977, the Big Ear radio telescope in Ohio recorded a 72-second burst at 1420 MHz, 30 times stronger than the background. Jerry Emmons circled the printout and wrote, "Wow," in the margin. The signal came from the direction of Sagittarius, right at the hydrogen line. It's never been repeated, and to this day no one knows what caused it. These episodes are more than stories. They're reminders of how easily hope and skepticism collide in radio astronomy. Natural phenomena can mimic the patterns we're trained to watch for. Interference, new astrophysical objects, even software quirks have all been mistaken for signs of intelligence. Each time, the scientific community has responded with a mix of curiosity and caution, demanding independent confirmation and careful analysis before drawing conclusions. The lessons from these signals linger in every new search. Extraordinary claims demand extraordinary evidence. Yet the thrill of the unknown remains. The possibility that a real message could hide in the noise keeps operators listening, decoding, and arguing late into the night. In this field, skepticism isn't just a guardrail, it's part of the adventure. Speculation takes hold as the operators study the binary grid, each pixel a possible clue from a distant mind. The left edge forms a spiral, arms curling in a way that recalls the familiar shape of a galaxy. It's not a perfect match for Andromeda or the Milky Way, more like a simplified emblem, a symbol that could stand for any spiral galaxy in the universe. Alongside the spiral, a column of dots and dashes seems to fall into a recognizable sequence. Some count 5 distinct groupings, each corresponding to the atomic numbers for hydrogen, carbon, nitrogen, oxygen, and phosphorus. These elements are the backbone of life as Earth knows it, and their presence in the pattern feels deliberate, as if the sender wanted to say, "We share the same chemistry." In the bitmap center, a cluster of marks repeats in a way that defies random noise. To some, the arrangement echoes the geometry of viral capsids or the double helix of DNA, shapes that appear in biology here and perhaps everywhere. Others see a mathematical constant, maybe pi or a Fibonacci progression woven into the grid. There's even debate about a possible countdown or recursive sequence, a motif that could be a warning, a greeting, or simply a marker of artificial origin. None of these interpretations are certain. The group is careful to flag every guess as hypothetical, aware that meaning can be conjured from patterns where none was intended. Still, the combination of universal symbols, galactic structure, elemental codes, and mathematical regularity invites the imagination to run wild. The message, if it is a message, feels built to cross the gulf of language, time, and biology. For the operators, the thrill of recognition is shadowed by the question of intent. What does it mean to receive a signal that seems to know how to be understood? Andromeda hangs in the sky as a familiar patch of faint light, but its true presence is measured in distance and motion that defy human scale. The galaxy sits 2.5 million light-years from Earth, so far that the radio pulses arriving now began their journey before the first humans walked upright. Every bit of information carried by the signal has crossed a gulf where continents shifted, species rose and vanished, and the planet itself changed beyond recognition. The numbers are almost too large to hold in mind, 2.37 times 10 superscript 2 superscript 2 meters, a span so wide that even light, the universe's fastest traveler, needs 2.5 million years to bridge it. Andromeda is not a silent neighbor. It approaches the Milky Way at about 110 kilometers per second, drawn by gravity toward an eventual collision billions of years in the future. The two galaxies will one day merge. But for now, the gap between them is a kind of cosmic abyss. Any message sent from there is a message from the deep past, echoing forward without hope of reply. Even if a response were possible, it would take 5 million years for a round trip, longer than the span of all recorded human history multiplied 1,000 times. The senders, if they ever existed, are gone. The world that receives their signal is not the one they addressed. This is not a dialogue, but the discovery of a message in a bottle, cast into a current that cares nothing for the fate of its sender or the questions of its receiver. The scale of the contact is overwhelming, not just in light years but in the realization that across such distances, even communication becomes a kind of fossil, preserved by time but stripped of context, suspended between two worlds that will never meet. In 1977, the WOW signal lasted just 72 seconds, yet it still fuels debate decades later. This documentary has shown how amateur radio operators worldwide can detect and verify anomalies on the hydrogen line using real-time data sharing and established scientific protocols. The Andromeda galaxy, at 2.5 million light-years away and approaching our Milky Way at 110 kilometers per second, remains a statistically promising but largely unexamined SETI target. The technical barriers to detecting a signal from that distance are enormous, and no confirmed extraterrestrial message has ever been received. Despite rigorous verification methods and the caution of professional astronomers, the central question persists. Are we missing signals from distant galaxies simply because we are not looking in the right place or with the right tools?